All right, this is going to be a video where we're working through example problem 5-13, example 5-13, and this is on page 246 in the book. All right, for this problem, we're looking at, once again, a rigid tank. So we have an insulated. When you see the word insulated, that should automatically jump out as being adiabatic, where our heat transfer is going to be equal to 0. An insulated 8 cubic meter rigid tank. So this should alert you to the fact that we're not going to have a change in volume. Contains air. So this should tell you that we have an ideal gas, or something close to an ideal gas. We're going to use the ideal gas law at 600 kilopascal and 400 degrees Kelvin. A valve to the tank. A valve to the tank is opened, and air is allowed to escape. The air escapes until pressure is 200 kilopascal. The temperature of the air is held constant by an electrical heater. Determine the electrical energy so the work done by the electrical heater required. All right, so we have a model of this problem in the book where we have a rigid insulated tank that has a valve at the top that's open, and it allows air to escape until the pressure is at 200 kilopascal. Our temperature and our volume do not change, and we don't have any heat transfer since this is an insulated tank. All right, so for this problem, we're making a few assumptions. Our assumptions are that our potential energy and kinetic energy are going to be negligible when compared to the enthalpy and internal energy of the system. We are also going to assume that we don't have any mass coming in. We only have mass coming out. We don't have any inlet here. We only have an exit. We're also going to assume this is an unsteady but uniform flow through the exit. We're also going to assume that air can be modeled as an ideal gas using the ideal gas law. And from table A1, we're going to find that the gas constant associated with air is going to be 0.287 kilopascals cubic meter per kilogram Kelvin. All right. I think that's all the assumptions that we need to make for this problem. So we can go ahead and get started. We're going to take advantage of the two equations that I presented in chapter 5, part 3's video. So our mass balance will first be here, mass balance. And this equation is the mass of our system is equal to the mass in minus the mass out. As we said before, this can also be M2 minus M1 of our control volume is equal to our mass coming in minus our mass exiting. In our assumptions, we're assuming we don't have any mass coming in. This will go to 0. So our equation will be M2 minus M1 is equal to negative M exiting. If we rearrange the negative signs, we have M exit equals M1 minus M2. So this is our mass balance equation for this problem. And let's move on to an energy balance equation. So energy balance, a little more complicated, but much more fun. Here we have our energy balance. And similar to mass, we're gonna start with the equation that a change in energy of our system is not equal to 0. We're in an unsteady flow, but it is equal to our energy coming in minus our energy coming out. And as we said before, this is going to be M2 minus specific energy at point 2, sorry, that's a 2, minus M1 specific energy at point 1. And then we're going to have our heat coming in plus our work coming in plus the summation of all our flow energies minus the same thing coming out, heat out plus work out plus a summation of all of our flow energy coming out. So in our assumptions up here, we stated that kinetic and potential energy were equal to 0. So when we have kinetic and potential energy equal to 0, our specific energy equation is going to reduce down to only internal energy. And our flow energy is going to reduce down to only enthalpy. And this is because our specific energy equation is kinetic energy plus potential energy plus internal energy. So when these go to 0, it's just equal to U. And our flow energy is equal to enthalpy plus kinetic energy plus potential energy. When these go to 0, it's only equal to enthalpy. So this is just as a note to help refresh you. All right. We are also assuming that we do not have any mass coming in, which means that this entire side of the equation here is canceling out for some of our mass flow coming in. We know we have work coming in. This is in the form of electrical energy, but we are an adiabatic system, well insulated, no heat transfer occurring. We also are not making work by capturing some of the energy coming out of this valve. We're not putting this into a turbine or anything, getting any work out. We only have this electrical energy coming in. All right, so now we have a lot of things reduced here. We can form the equation M2U2 here minus M1U1 here is going to be equal to our work in, which is electrical work. And then what else do we have remaining? We have some outcoming mass leaving the system. So minus our mass exiting times our enthalpy exiting. So as a reminder, we're using internal energy and enthalpy in terms of specific energy and flow energy here and reducing down the equation. So the problem statement is asking for us to determine the electrical energy supplied. So we are trying to isolate electrical energy here. Our equation becomes our work in, which is our electrical work done by the heater to keep the air at a certain temperature, is going to be equal to mass exiting, enthalpy exiting, plus mass at the exit, internal energy at the exit, minus mass at the inlet, internal energy at the inlet. So this is our energy equation for the problem. Okay, so enthalpy and internal energy, you should immediately realize that this is going to require looking up in the table. We can look up with known temperature, which is not changing over time, and we also have the pressure at the starting condition and the ending condition, so it's easy to look up enthalpy and internal energy. What we need to solve for first would be mass. So how are we going to solve for mass? There are assumptions that we made right up front to make our solving for mass a bit more straightforward. So we're assuming that the air in this tank, we can use the ideal gas law for, and we already looked up the value for R. So if we look here. Let's try to solve for mass coming in at point 1. So mass at point 1 will be equal to the pressure at point 1, volume at point 1. And this is an uppercase volume because we're including mass here. It's not specific volume. Our gas constant and our temperature at point 1. So we know our pressure at point 1 is going to be 600 kilopascal. Our volume at point 1 is 8 cubic meters. Our gas constant is 0.287 kilopascal cubic meter kilogram Kelvin. 0.287 kilopascal cubic meter kilogram Kelvin. And our temperature was given as 400 Kelvin. We don't even need to convert to Kelvin this time. All right, so plugging this into your calculator, you should get something close to 41.8 kilograms. And then we would just keep doing the same thing for our mass at point 2, which would be P at point 2, volume at point 2, same ideal gas, and then our temperature at point 2. So our volume, temperature, and R are not going to change. You can just keep those in your calculator and change your pressure to be equal to 200 kilopascal. 200 kilopascal, 8 cubic meter, volume not changing, 0.287 kilopascal, cubic meter, kilograms, Kelvin, and then 400 degrees Kelvin. And this is going to be equal to something close to 13.9 kilograms. So we have our mass at point 1, our mass at point 2. The only mass that we're missing from this equation would be our mass at the exit. So our mass at the exit, we know, is going to be equal to what we set it equal to in our mass balance equation up front. So our mass exiting is equal to the change between mass at point 1, mass at point 2. So we know that our M exiting is equal to M1 minus M2. We just solve for these two. So this is 41.8 minus 13.4 kilograms, which gives us 27.4 kilograms. Is that correct? 6, I think. Well, close enough, kilograms. All right, let me just do this math over here. I think I might have typed in my calculator wrong. So 4, 8, 28.4. 28.4. All right. Oh, I see the mistake I made. Okay. So I believe this is 13.9, not a 4, which is where that mistake comes from, 13.9. And then with 13.9 here, that's why it's not matching in my calculator. All right, so now we have 41.8 minus 13.9. This is going to be 27.9. All right. 27.9 kilograms is going to be our mass at the exit. So now we have our mass 2, our mass 1, and our mass at the exit. All right. Now we're going to need to look up our internal energies and enthalpies for this problem. So in order to solve this equation, we now have our mass at the exit, M2, M1. We need internal energy at point 1 and point 2, and enthalpy at point 1. Nope, at the exit. All right, so turning to the back of the book, we know that we're going to go to the table for air, which is going to be table A17, Let's see here. Okay, A19, A17. Here we go. So this is for ideal gas properties of air. And when we're looking at our temperature, which is going to be 400 degrees, we can see that we have, oh, sorry, BT. All right, so our enthalpy at 400 degrees is going to be 400.98 kilojoules per kilogram. And our internal energy at 400 Kelvin is going to be 286.16 kilogram per kilojoule. And there's not much else we can tell from this table. All right. So coming back to our problem here, we are still trying to solve for this equation. We now have our enthalpy at 400 degrees Kelvin. We were able to look up our internal energy, but did we look up internal energy? Oh, I'm sorry, I'm off the page. Did we look up internal energy for 0.1 or 0.2? Think about it for a minute. And we actually looked at the internal energy for both of these. Internal energy for one is going to be equal to an internal energy at 0.2. These are both going to be the same because the air is being held at a constant temperature. So the internal energy is going to be staying the same. It's forced to stay the same by this electrical work that's coming in. So now we have everything that we need to solve this problem. We have our equation for our work in is MEHE plus M2U2 minus M1U1. So our mass at the exit is 27.9 kilograms after a little bit of a struggle to find that number. Our enthalpy is 400.98 kilojoules per kilogram. And then our mass at 0.2, we found to be 13.9 kilograms. Our internal energy is going to be 286.16 kilojoules per kilogram. And then our mass at 0.1, oh, this is a minus. Our mass at 0.1 is 41.8 kilograms. This is going to be multiplied by the same internal energy. It's forced to stay the same with the heating. And solving for all of this together, we get about 3,200 kilojoules, roughly. Which is the electrical energy required by the heater. Electrical energy required by heater. And it's good to note that this is a positive because we have heat coming into the system, work coming in by the electrical heater. All right, so as I mentioned, this problem is on page 246 and 247 if you need some additional guidance on how this was solved. And I think that is all for this problem. So please email me with any questions or concerns, and I will post some follow-up information shortly. Thanks. Have a good one.